Hi everyone, myself Saket and my group members Hemasai and Sharda. We are group 2 and our project is flight price prediction using machine learning algorithms. In this, we will show how we built an airfares prediction system that's not just about getting good numbers but about evaluating models correctly over time, avoiding data leakage and making the whole workflow transparent and reproducible through a Streamlit app. Yeah, here's, here's the roadmap for today. We'll start with the problem and objective, then explain why leakage safe evaluation is so important for airfare. Then related work. Next, we'll go through the dataset and features, our pre-processing and chronological split, and the overall system architecture. After that, we'll introduce the models we used, show results and diagnostics, and talk about our statistical significance test. Finally, we'll touch on reproducibility and the app, present conclusions and future work, and then do a short live demo. Our problem is to predict the average market fare for a route carrier quarter combination. We use features that are easy to interpret in airline context. The route, carrier, the distance between airports, passenger demand, and the time period. Our object, our objective is not just to fit past data, but to forecast realistically into the next time window. So everything we do is geared towards answering the question, if I train on past quarters, how well can I predict fares in future quarters? Yeah. Related work. Yeah. So let me quickly place our project in the context of our previous work. Several pages use classic machine learning models on airfare or ticket price data. They show the models like linear regression, random forest, gradient boosting, and extra trees can work very well on tabular airfare features. But the performance is quite sensitive to how you engineer features and how you evaluate those models. There's also work that pushes deep learning for flight prices. GRU-based models and attention mechanisms have been used on richer, high-frequency price sequences and often beat simple baselines in those settings. But they typically assume more detailed time series and require a lot of tuning and data than we have in our quarterly market level problem. Finally, broader studies on tabular learning and evaluation make two key points. First, for structured tabular data, tree ensembles are often as good as or better than generic deep networks. Second, for time-dependent problems, you should not use random split because they leak information for future and they overly optimistic metrics. Chronological or block splits give us more honest estimates. Our project is designed around these lessons. We focus on clean, interpretable tabular feature set. We benchmark five classic regressors with an emphasis on tree ensembles, and we use a skirt leakage safe chronological split instead of a random one. On top of that, we add statistical tests and from scratch implementations of three algorithms to make the whole pipeline transparent and easy to trust. Airfare is highly time dependent. Fuel prices, seasonality, and the economy all change over time. If we simply do a random train test split, we can accidentally give the models information from the future in the training set. That kind of leakage makes the model look unrealistically good, but it wouldn't perform that well in real life. So we enforce a strict chronological train validation test rate, and we fit all the pre-processing steps only on the train window. The diagram here shows how that we moved forward in time, past through, middle to future, and we explicitly avoid any random shuffle. Our contribution fall into few parts. First, we built a leakage-safe pipeline on DB1B derived quarterly data. Secondly, we benchmarked five regression models under one shared pre-processing pipeline so that the comparison is fair. Third, we coded from scratch versions of linear regression, KNN, and decision trees and checked them against skip-learn for parity. Fourth, we added statistical testing, a top two pair test on the test set, and Friedman plus Wilson home analysis and cross-validation polls. And finally, we wrapped all of this in a Streamlit app that supports diagnostic prediction and exporting aircraft for reproducibility. This is a preview of a clean dataset. Each row represents a single route carrier quarter combination with associated demand and fare information. Key fields include the carrier group, origin and destination, airport IDs, great circle distance in miles, quarterly passengers, the year and quarter, and the average market fare. We intentionally kept the schema compact and unpredictable so that each feature has a clear business meaning and the model behavior is easier to understand. Here is a summary of our pre-processing pipeline. For numeric features, we used median imputation, which is robust to skew and outliers. For categories, we use most frequent imputation, so we didn't invert fake categories. We also apply winsorization only on target fare, capping extreme tails so a few bad records don't dominate the loss. We one hot encoded quarter and carried, and we standard scale numerics features like distance and passengers, which is crucial for Canaan and linear models. Finally, we enforce a 70-10-20 chronological split and fit all pre-processing only on the train set. Then reuse those transformations for validation and tests. This diagram shows how everything fits together. At the top of the start, from the raw DB1B derived dataset and run a cleaning and pre-processing stage to produce a single clean CSV. That flows into our baseline training step, where we train the five fit-learn models and our custom models inside a shared pipeline, then save metrics, plots, models, and a configuration file. Those artifacts are then consumed by a Streamlit web app, which exposes pages for dataset exploration, results, implementation checks, prediction, and export. The key idea is the same split, preprocessing, and seeds are used throughout. So what you see in the app matches what we describe in the report. So next, my teammate Hemasa is going to continue.
Okay, let's see the models and algorithms. We choose models that cover different behaviors on tabular data. We have linear regression as a transparent, interpretable baseline. The K nearest neighbors captures local similarity markers that look like should have similar fates. A decision tree learns if then rules and feature interactions. Random forest averages many trees to reduce variance, and gradient boosting adds small trees step by step to reduce bias. We choose linear regression, k nearest neighbors, and decision tree for the Scratch implementation because they model a distance-based non-parametric model and a tree-based rule model, and each has clean, well-defined math that is realistic to implement by hand. The more complex ensembles like random forest and gradient boosting rely heavily on optimized library code. So we kept those as library implementations only. Let's go to the training setup. All models share the same chronological split. As we discussed earlier, it's 70% train, 10% validation, and 20% test. They also share the same column transfer pipeline. Median numeric imputation, most frequent categorical imputation, one hot encoding for quarter and carrier, standard scaling for numerics, and winsorization on the target fare only. Our selection rule is simple. We pick the model with the lowest validation RMSE, then we report test metrics once without tuning on test. We also log fit time and predict time per row for each model so we can talk about both accuracy and speed. Let's see the linear regression. We use the linear regression as a very transparent baseline. It predicts fare as a weighted sum of the features plus an intercept, choosing the weights that minimize squared error. Here we use scikit-learn's linear regression with standardized numeric features and one hot categories all inside the same pipeline. In the predicted versus true plot, you can see that it does quite well in the mid-fare range, but it struggles on extreme high fares, where the relationship is more non-linear. So it's great sanity check model, but it can't capture all complex patterns. Let's discuss about the k nearest neighbors. The k nearest neighbors takes a different approach. Like it doesn't learn global F coefficients, it just looks up similar past cases. For a new market, it finds the seven nearest neighbors in scale feature. like scale feature space and predicts the average fare of those neighbors. This makes KNN a nice local non-parametric baseline with minimal assumptions, but predictions are slower because it has to search the training set. In our results, it behaves reasonably in the mid-range, but we see pockets of large residuals for long haul, they are strongly seasonal routes where the nearest neighbors are not truly comparable. It also reminds us why correct scaling is so important for distance-based methods. Let's go for the decision tree. We added a decision tree to capture readable if-then rules and feature interactions. The tree recursively splits the data to reduce mean squared error, stopping when it reaches a maximum depth or minimum leaf size. In our case, we capped depth at 8. This helps avoid extreme overfitting, but the model still produces piecewise constant predictions, which show up as visible bands in the predicted versus true plot. The tree does learn useful regimes like short haul versus long haul, but as a single tree, it has higher variance than ensembles. So overall, it's weaker than random forest or gradient boosting. Let's go for the random forest. Random forest is our strongest tabular baseline. It trains many decision trees on bootstrap samples of the data and uses random subsets of features at the e-split. At prediction time, it simply averages the predictions from all trees, which reduces variance and smooths out individual overfits. In our experiments, random forest achieves the lowest validation RMSE, about 59.17, and it is very stable across folds. The predicted versus true plot shows a tight diagonal for common fares, residuals are centered near zero with moderate spread at high fares, and interference remains fast at roughly 0.096 milliseconds per row. Let's go for gradient boosting. Gradient boosting focuses on reducing bias by building the model step by step. We start with a simple initial prediction and then repeatedly fit shallow trees to the residuals. The mistake of the current model with a learning rate that controls how big each step is. Here we use a conservative configuration with 100 trees and learning rate 0.1%. Gradient boosting comes very close to random forest on validation or MSC, but it achieves the best test MAE on the held out period. Our top two paired T test shows that this test MAE advantage over random forest is statistically significant. Let's go for the validation and test. This like this slide will summarize about the main metrics. Our primary selection metric is validation RMSE. So by that rule, random forest is the winner with roughly 59.17. Gradient boosting is close on validation but clearly better on test MAE. Linear regression is fast and fairly accurate but less stable across folds. And the single tree and KNN lag behind the ensembles. So in this project, random forest is our default model by the selection rule, while gradient boosting is highlighted as an alternate that generalizes slightly better on the specific test window. So my teammate Sharda will continue the remaining slides.
Now let's see about the diagnostics because just looking at metrics isn't enough. Here we are looking at random forests predicted versus true plot and the residuals versus predicted plot. In the predicted versus true chart, we can see a nice tight diagonal band for the usual mid-range fares. That's what we want. And when the fares goes up, our predictions go up with it. As we move into the very high fares, that cloud starts to spread out more. That actually makes sense because those long haul or peak season routes are much rarer and naturally noisier. On the residuals plot, most of the points are centered around zero, which tells us that the model isn't systematically over or undercharging. The spread of the residuals grow as the predicted fare gets larger, which is which is the classic bigger values, bigger noise pattern, which we expect in an airfare data. Taken together, these diagnostics tell us that the model is behaving in a realistic way, not doing something weird just to chase the metric. Since this is a category C project, we can't just say that a model A is better than model B based on raw metrics. We need to check whether the observed gaps are likely to be real or just noise from a particular split. So we use two complementary statistical views. First, a top two paired test on the held out test set, and second, an all model cross validation analysis using a Friedman test followed by Wilcoxon best versus others with whole correction. Together, these let us talk about significance both on the final test window and across folds. On the test set, we directly compare random forest versus gradient boosting on per window absolute errors. We define a difference of MAE as random forest error minus gradient boosting error. The difference in MAE is about plus 3.05, which means gradient boosting's MAE is lower by around $3, and the p value is roughly 1.9 into 10 to the power minus 0.9 with a 95% confidence interval that is fully positive. So for this particular test window, gradient boosting is statistically significant MAE advantage over random forest. For the cross-validation view, we run a shared five-fold CV for all five methods. We apply a Friedman test to the fold-wise MAE and RMSE scores, which detects that there are overall differences among models. Then we run Wilcoxon signed rank tests, comparing the best model against each of the others, and we adjust the p-values using home correction. With only five-fold, this correction is conservative and the adjusted p-values are non-significant at the 0.05 level. So the interpretation is that random forest leads on the folds, but the pairwise gaps are small and not statistically conclusive after correction. This slide shows the full cross-validation significance panel from the app. At the top, you can see the box plot of MAE across folds for each model, which usually confirm that random forest tends to be the lowest. Below that is the Friedman test result and Wilcoxon home table. We used this slide in the demo to walk through the exact numbers, but the key message here is that there are meaningful differences overall, but with five folds, we avoid overclaiming that one model is significantly better than other across folds. To make our work reproducible, we export all of the key artifacts from the run. This includes metrics.csv, which contains all validation and test metrics plus fit and predict times. We also export a config.json file that stores the dataset fingerprint, split description, feature schema, pre-processing choices, and model hyperparameters. These files allow anyone to recreate the run, verify that the app and the report are consistent, and build on top of our system. We will see the demo of our project now. So let's now take a look into our app. So our app opens up with the dataset page. So here is an overview of the dataset. At the top, you can see the preview of the cleaned DB1B derived dataset. Each row is a route carrier quarter combination with distance, passengers, quarter, year, and the average fare. I'll scroll a little bit here so you can see the whole structure. And below here, we have the pre-processing summary with median imputation for numerical fields, most frequent for categoricals, one hot encoding for quarter and carrier, and the chronological 70-10-20 split. This page is mainly here to show that the app is using the same leakage safe pipeline that the report and the presentation talks about. And we also gave a little numeric summary for the users. Moving on to the results page, here we have the leaderboard and diagnostics. So this is where we benchmark all five models under the same pipeline. The leaderboard table shows validation and test metrics like RMSE, MAE, R square, plus fit time, and per row prediction time. So our selection rule is choose the model with the lowest validation RMSE. So you can see random forest is flagged as the top model here. And here below, I can choose a model for diagnostics. So here I'll keep it as random forest as selected. So And below, we'll be able to see the predicted versus true plot, which shows a nice diagonal band in the common fare range and more spread in the very high fares, which matches the long tail behavior we expect. Below, and beside it, we have the residuals versus predicted plot, which shows residuals centered around zero with variance increasing for higher fares with that heteroscedastic pattern we mentioned earlier. And when we scroll further, we will be able to see the top two significance test on the test set. Here we're just comparing our two best models, random forest and gradient boosting. Um, so on the right side, we are able to see the difference of MAE between random forest and the gradient boosting, which is around 3.0518. So this means that we literally took the absolute error of random forest minus the absolute error of gradient boosting for each row and then averaged it. Because this value is positive, it means gradient boosting's MAE is about $3 lower per observation than the random forest on this test set. On the left, you can see the p-value from a paired t-test on those per row differences. It's around 1.9 into 10 to the power of minus 109, which is effectively zero. And the 95% confidence interval down here is fully positive as well. And the interpretation here is very simple. On this final holdout test window, gradient boosting has statistically significant MAE advantage over random forest. That's why the green banner at the bottom says gradient boosting outperforms random forest with lower error. And scrolling down further to cross-validation significance, we have two options to select from, which is MAE and RMSE. So for the cross-validation significance section with metric of MAE, we see the box plots of MAE across 5 folds for all the 5 models. So from the plot, we can see that random forest is down here with the lowest median MAE and the tightest spread. Gradient boosting is just above it. Linear KNN and decision tree sit higher. Underneath, we run a Friedman test, which checks whether there are overall differences between the models across folds. The chi-square value is 20 and the p-value is about 0.005. So we say that across these shared folds, the models are not all the same. There are real differences in MAE. On the right is the Wilcoxon plus home table, where we compare each model to the best, where that's random forest in our case. The difference of MAE, which is model minus the best column, shows how much worse each model is on average compared to random forest. All those numbers are positive, which again says that random forest has the lowest MAE. But the important part is that is the P adjunct column. After applying home correction for multiple comparisons with only 5 folds, all the adjusted p values are 0.125, so they are marked NS for not significant. So our cautious conclusion for MAE is random forest looks best across folds, but the pairwise gaps are not statistically significant once we correct for multiple tests. Now we toggle the cross-validation significance to RMSE. So here we can see a very similar picture where random forest has the lowest median RMSE in the box plots. Gradient boosting is second and the others are higher. Here again, the coming below, the Friedman test shows it has a small p-value, so there are overall differences in RMSE. In the Wilcoxon plus home table on the right, the difference of RMSE column shows that every other model has higher RMSE than random model, but after home correction, all the adjusted p-values are 0.125 and marked NS. So the RMSE for the RMSE, we could say that random forest is the fold-wise leader, but the advantages across folds are not statistically conclusive with the small number of folds. Putting everything together, validation says that random forest is our default choice with lowest RMSE and stable across folds. Whereas a test set top to view says gradient boosting wins on MAE on the final unseen period, and that advantage is statistically significant. We show both views in the app, so we are transparent about the models and are doing that we are doing, and we don't overclaim based on single metric or single split. Moving on to the implementation check page. Here, we compare our from-scratch implementations of linear regression, k-nearest neighbors, and decision tree against the scikit-learn versions under the exact same pre-processing and hyperparametrics. The table shows the RMSE and MAE differences and a simple status flag. All of them are within a tiny tolerance and are marked matches, which tells us our custom implementations behave the same as that of the library models and the theory we implemented are correct. Moving on to the prediction page, we have a prediction console. It takes a little bit of time to load all the models into the console. So here is the loaded page, completely loaded page. So this is where a user can try what if scenarios. And for our demo, I'll choose a carrier from the dropdown. Let's say it's AS. And for the quarter, maybe I'll select 2. And for distance, let's keep it at 1,000 miles. And for passengers, it should be about 150. And let's click on predict fare and see what happens. So clicking on predict fare, the app returns the predicted fare for the selected model along with the inference time. So if I click on the show all models comparison and then click on predict again, so this will load every model. Here we get a small table of predictions from all 5 models for the same input. That's useful for quick sanity checks and for explaining how different models behave on the same route. So moving on to the export page, this is the last page of the app. From here, the user will be able to download a metrics.csv and a config.json file. The config file contains the dataset fingerprint, the split description, feature schema, pre-processing parametrics, and model hyperparameters. Together with the metrics and plots, that's everything someone would need to reproduce the results in the report or audit our claims. So clicking on the download button would go ahead and download the CSV or the JSON file that someone would need. This is the end of our demo, and this almost wraps our overall leakage safe pipeline, the model comparisons, and the statistical tests into a single reproducible tool for airfare prediction. Let's now go back to the presentation. Okay, coming back to the presentation, let's move to the future work. Looking ahead, there are a lot of ways we could grow this project. First, we'd like to add richer features, things like holiday flags, more detailed time indicators, fuel price indexes, and some measures of competition on a route. Those could help explain some of the tricky fare swings we still see. On the modeling side, we could try stronger methods such as XGBoost, Light GBM, or even neural networks, and also add prediction intervals so we can say not just one number but a range of likely fares, especially for extreme cases. And from a systems point of view, we'd love to push the app closer to a production tool, handling larger data sets, refreshing with new quarters automatically, and maybe offering route specific forecasting views for analysts. To wrap up, here is the big picture. First, random forest was our strongest model overall when we followed our rule of pick the best validation RMSC. It was also the most stable across cross validation folds. So that's the one we treat as our default. Second, gradient boosting actually did a little better on the final test set in terms of MAE. When we ran the top 2 significance test, that difference in test MAE was statistically significant, so it's not just random noise on that split. Third, the diagnostics plots looked very realistic, where the model behaves nicely on common fares and shows higher but expected variance on those rare high fare routes. And finally, the most important part for us is the pipeline and the app. The leakage safe design, the shared pre-processing, and the Streamlit interface gives us a clean, reproducible way of evaluating and comparing airfare models instead of just throwing numbers into a table and hoping they're fair. I hope this presentation was clear, and thank you for listening. Thank you.